Welcome to YourTown television program. My name is Jeff Kline. This segment is sponsored by the Naval Postgraduate School Foundation, and we like to bring you interesting people and research associated with the school. Today, our first segment is with Dr. David Alderson, who is the director of our Center for Critical Infrastructure Defense, and we'd like to talk to him about his field of operations research and why that's critical in today's homeland security environment. Dave, welcome to the show.
Thanks for having me, Jeff.
The first way we start off most of our shows is to find out a little bit more about our guests before we delve directly into the work you're doing for the postgraduate school. So what about you? What's your background? Where are you from originally, and where did you go to school?
So I grew up in the northeastern United States, went to college on the East Coast, and ultimately made my way to California for graduate school at Stanford University.
Oh, so you got your PhD at Stanford?
I did. That's where I did my doctorate work.
And what did you study?
So I studied operations research, which is what I now work in here at NPS.
Oh, so you have a PhD in operations research.
That's right.
Well, how many faculty actually have PhDs in OR in our department?
So we actually have one of the largest OR departments in the world. It's a curriculum that dates back to 1951. We've got a faculty of a little more than 40 different faculty members, over half of which have PhDs.
Okay, great. And well, tell us a little bit about the field of operations research. What
Sure.
is it?
So operations research is a field that actually grew up out of World War II. It was a collaboration originally between the Americans and the Brits, and it started with a pretty straightforward realization. The idea was that if you're only going to do something once, maybe there's not that much that the scientific method can be used to help.
But so what do you mean by the scientific method? I'm sorry.
Well, the scientific method is really about observing, experimenting, and deciding, right? So it's a process by which we discern or try to discern truth, or more accurately, we sort of disprove things that we learn not to work.
But it's repeatable, and in this case, most decisions we make aren't in some cases.
That's right. And so the key idea going back to World War II is that they were doing certain things over and over and over again. And operations research really grew up as an application of the scientific method to repeated operations. And this was used then in World War II for things like hunting Nazi U-boats in the North Atlantic, pre-positioning aerial defenses for the Battle of Britain, large-scale logistics in support of the war effort, so on and so forth.
So we became one of the largest OR departments. And what attracted you to us at Naval Postgraduate School?
Well, so for that I have to go back just a little bit. So you asked where I started.
Right.
And actually out of college, I worked first on Wall Street for a number of years.
Oh, that must have been exciting.
It certainly was.
Well, now wait, that was before or after you got your PhD?
That was before, right?
Okay.
So after my undergraduate degree, I went to Manhattan, lived in New York, and worked on Wall Street for a number of years. And I was building technology for one of the big banks, so we had an in-house trading system. I was a part of a team that was developing that. And one of the things that really interested me about that work was that the technology that I was working on was used in all of our regional offices. So it was being used in New York and London and Zurich and Frankfurt and Hong Kong and Tokyo. And so what I was observing, this is more than 20 years ago now, was that what happened in one place affected very much what happened in another place. And so while I ultimately decided that a life on Wall Street wasn't for me, when I moved west to Stanford for graduate work, I had this idea in my mind that this interconnectedness that was very much starting to shape our lives was perhaps important, right? This was a time when the internet was just starting to take hold. Yahoo was a big thing back in the day back then. And so when I arrived to Stanford, I asked what in retrospect was sort of a very naive question. I asked my professors, so are there people who are starting to think about things like road systems and telecommunication systems in kind of this very interdependent and networked way.
And so connected ways.
In a connected way. And so it turned out that not only were people starting to think about it, but President Clinton had commissioned a committee to study exactly this problem. So this is called the President's Commission on Critical Infrastructure Protection. And so this was a group of folks from government, from academia, and from industry who were charged with starting to think about what's now been known as critical infrastructure. So these are things like roads and bridges, water systems, telecommunication systems, transportation systems, systems that are so vital to our way of life that if they were to be disrupted in any significant way for any period of time, it would seriously affect the welfare of our country.
Now, this was pre 9/11, right?
Absolutely.
So what was the motivation for President Clinton to do this? Just the concern about the fragility of the infrastructure system?
Yeah, so that's right. So this report was ultimately published in 1997.
Right.
And the original motivation for this commission was, one, the recognition that the internet was starting to become important in ways that folks were only starting to appreciate. And so you had all these different largely independent infrastructures, right? Things like road systems, again, and telecommunications, water and whatnot. They had grown up on their own, but they were now becoming more and more interdependent, with the internet as sort of becoming a central nervous system. So what you could start to see is that a problem in one infrastructure would now start to cause problems in another infrastructure.
Like a cascading type thing?
That's exactly right. Cascading failures, cascading effects are the things that folks talk about.
So a similar example would be the electric power grid system going down in one area, affecting a large portion of the United States.
Absolutely. Not only affecting other parts of the electric power grid, but affecting other things, right? Affecting maybe water systems because you need pumps, or fuel systems, or banking systems because the ATMs don't have power so people can't get their money. You can't process financial transaction, these kinds of things. So what was really interesting to me at the time, again, as a graduate student, I got to actually participate in some of these meetings by this presidential commission. I was the grad student in the back sort of taking notes. And I remember at a big meeting at Lawrence Livermore National Labs, right, just over in the East Bay, following the final recommendations, there was a presentation on science and technology, and it was a presentation being given by former president of the lab, who was a Nobel laureate in physics. And essentially what he said is, you know, from a science and technology perspective, we have no idea what's going to happen. We recognize that these things are all more and more interconnected, and we really don't know what the future holds. And so when you're a graduate student and you hear, you know, one, interesting, important problem, and two,
nobody
knows what's going to do. That's
that
sort of
invites research and
that
dissertation.
is an opportunity. And so so that's been the last 20 years of my life, more or less, and will be the next 20 almost certainly.
Well, would you describe this as the systems you're talking about? And it's directly related to your position as the director of this Critical Infrastructure Defense, the Center for Critical Infrastructure Defense. But these are complex and sometimes chaotic systems, particularly the interdependencies from them, so they're very hard to predict.
Prediction's certainly a challenge. So they are big in scale and scope. They tend to be regional in their nature. They operate at very different time scales. What I mean by that is you have some systems like electric power and the internet that are operating at fractions of a second, and you have other systems that are operating maybe on the order of minutes, like traffic on the freeway building up. You've got other systems that are operating at hours. And then you've got other things that happen over much longer periods of time, days, weeks, months, and years. So building infrastructure takes a long time. And so a challenge is, how do we go about designing and building infrastructure that's going to last us a very long period of time, even though the technology underlying all this is changing so rapidly.
So after that great explanation, what was your dissertation about then?
So my dissertation was largely trying to frame this problem of critical infrastructure defense.
Right.
It wasn't a subject of study necessarily back then. And so my dissertation was largely about framing this problem, describing it, and then I worked on a small modeling part of that. But that really ultimately led to a lot of follow-on work. So in particular, I started spending time at a place called the Santa Fe Institute, which is a Center for Complex Systems Study in Santa Fe, New Mexico. And then ultimately, when I finished at Stanford first, I went down to the California Institute of Technology and worked as a postdoctoral researcher for a couple of years before ultimately arriving at NPS.
That was a great prelude, but you didn't answer my question about what attracted you to NPS then.
So Monterey's always been a special place.
Sure.
So my wife and I actually got engaged at Point Joe over in Pebble Beach.
Oh, is that right?
That's true, yeah. So we had always thought at some point about wanting to come to Monterey, and initially the idea was, well, maybe it'll be when we retire someday, right? A lot of people move here to enjoy retirement. And ultimately, it was meeting colleagues at the Naval Postgraduate School, learning about the Operations Research Department, and understanding in much more detail the specific opportunities that it presented that ultimately brought us here much sooner.
Okay, so you've described the field of operations research. You've talked about the critical infrastructure that and the problem that emerged and what got you interested in it. How does operations research lend insight into the problem that you just formulated in our critical infrastructure defense? Or put another way, what does your center do, Dave?
Yes. So the reason that I ultimately wanted to come to NPS was working with colleagues who had been thinking about critical infrastructure actually for decades. And in particular, using a combination of operations research techniques called optimization. So essentially what we do is we build large-scale prescriptive decision models for how to operate these large systems. So that is, we build mathematical models out of which that make recommendations for how you should run the system in order to, let's say, minimize its operating cost or maximize its reliability or some other kind of thing.
Right.
And so we build these kinds of operations research decision support tools in support of a number of different kind of DoD operations. It turns out that you can do the same thing for critical infrastructure. So, for example, we might think about how the California Independent System Operator who runs the electric grid here in California might make decisions about how to maintain or change the connectivity of the grid, to decide which generators to turn on and turn off at any moments in time. To
Based
balance
on dynamic load.
Absolutely,
exactly.
right. Sure. So that's the starting point. But what we do here at the Naval Postgraduate School, which is a little bit different from most places, is we naturally have an adversarial perspective. So, so having to think about how to operate in the presence of a deliberate adversary is quite different than the way in which you might think about planning for natural hazard events or earthquakes, extreme weather, these types of things. And so what my colleagues here at NPS do is we look at our own civilian and military infrastructure systems from an adversarial perspective. That is, we essentially plan or think about from a targeting perspective, how would we deliberately interfere with these systems in the worst possible way? And that then leads to insights about where these systems are ultimately vulnerable and what we can do to make limited investments to make these systems more robust, to make them more resilient. And those investments can take the form of hardening certain components so that they can withstand certain types of insult, or maybe adding backups or adding more capacity. In some cases, it might mean actually building entirely new infrastructure, not just retrofitting what we already have.
Well, what is the difference between the technique of optimization that you're talking about and simply prioritizing critical components of a particular infrastructure? Let's take a water or fuel infrastructure. If my main pump is the most important thing, why not just protect it first and then move to the second most important thing instead of using the techniques you use?
Yeah, so you've identified sort of the second of three questions that most folks in government are interested in. The first one is, if a certain event were to happen, what would be the consequences? Consequences usually measured in terms of loss of function, damage, or maybe even loss of life. The second question always is, tell me what are the most important parts of my system? What parts are most critical? And then the third question is, what do I do about it? Right. So the second question about what's most critical, that's an important one, and it leads to what you would think common sense is, well, let me find the parts that are most important and simply put all my resources there. And the challenge is, or the thing that's important to understand about critical infrastructures as systems, is that it's the way in which components work together, not just individually, that matters. So let's take a simple example. I might ask you a question, how important is this bridge right here?
Right.
Well, it may depend on whether or not there's another bridge right next to it. It could be that losing one or the other bridge is not so bad because you have the other one that you can still use. But if you lose both the bridges together, it could be catastrophic. So it's the way in which components work together that ultimately is really important. And our techniques are designed to try to find that.
Well, you're implying that each system is must be uniquely analyzed because it may operate based on the way it's built and its purpose of its system.
That's exactly right, which means that we've got a lot of work ahead of us, right? So these systems are each different infrastructure sector. That is, electric power operates different from water, it operates different from transportation. And though on some level they all have a similar kind of network aspect, the way that they behave, the way that they respond, the way that they're designed is all very unique. And it means you have to study these in detail. The context for each individual system matters quite a bit.
Well, can you give us some examples of particular systems that you and your students have looked at in their center?
Yeah, so we have a forthcoming paper looking at the roads and bridges of the San Francisco Bay Area,
Wow.
trying to identify what are the most important points, most important bridges, most important tunnels in terms of routine
So similar
traffic.
to the example you just gave.
That's exactly right. Another one that we've been working on for the Department of Defense is looking at fuel distribution systems in the Pacific Theater. Right? So as you know, the Pacific Ocean is a very big place.
Right.
And in order for the United States Navy and the United States Department of Defense to operate there, both for combat operations, but also to do humanitarian assistance and disaster relief type of operations, it means that we have to have ships traveling great distances, we have to have aircraft traveling great distances, and all of that still requires a tremendous amount of fuel. And so what we've looked at is modeling the supply chain for military-grade fuels from the way in which they go from refineries throughout the world into theater and ultimately making their way primarily into ships and into aircraft. And so as part of that, we then are able to identify where are the key locations, where are those vulnerabilities, what's the worst thing that could happen if we were to lose certain assets, and then what do we do ultimately to try to make the operations, the movement of these fuels more robust, more resilient, so that we can make sure that we obtain mission success.
Well, that must be incredibly complex because the fuel system itself is composed of both crude, refinement system itself is complex. Then you have to have storage, movement. You have to get the fuel to the ships and airplanes at sea and that sort of thing. So
that's right.
And how are you studying the entire system or components of it?
So different studies will focus on different parts of it. If the system is too big to look in detail at the entire thing, but over the last 10 years or so, we've had students look at different parts of it. So for example, we'd have one student look at the fuel pipeline system on Guam. We have another student who would look at the fuel system on Okinawa. We had another student who looked at the multimodal fuel distribution system. That means moving things by barge, by pipe, by truck, by rail, in mainland Japan, right? So we take these little parts, pieces at a time, and then we can start to build them into a bigger aggregate view.
Well, we only have about 1 minute left, and I've got two questions for you.
Okay.
One is, we use specific systems as an example, but if you started work with two dissimilar systems, something like fuel and electricity or fuel and transportation, and talked about that interdependencies or dependencies that you referred to earlier in the show.
Yeah, so, well, I mean, that's in some sense the challenge going forward. Very much the state of the art is how do we start to build models that can analyze these interdependencies in a complicated way and do them at the scale of a large metropolitan region. Okay,
the last question I always ask our guests is, what do you like most about living in the Monterey Peninsula area?
So I love
besides getting a wife.
Yeah, so I love being here, a part of the community. I've got two boys, one in grade school, one in middle school, heavily involved in sports. So I've been coaching soccer and baseball and most recently lacrosse. So that keeps us very busy and is a lot of fun.
Well, Dr. Alderson, thank you very much for your contribution both to our nation and to our local community. And thank you for joining us at this segment of the YourTown television program. I'm signing off here as your sponsor, Jeff Kline, and hopefully join us again for learning more about the Naval Postgraduate School, its people, its research, and its interesting educational opportunities.